All right. Thank you. Bye. Hello out there, Australia. Jessica Allen here. I'm an ESD consultant with Suho, and I'm here to talk to you about air tightness testing and how we interpret the results that we get. Unfortunately, I have my backup laptop that we get. Unfortunately, I have my backup laptop that we get. Unfortunately, I have my backup laptop that we get. Unfortunately, I have my backup laptop that we get. Unfortunately, I have my backup laptop that we get. Unfortunately, I have my backup laptop that I backup laptop. Unfortunately, I have my backup laptop that's why unfortunately 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 I have my backup laptop. Maybe if I close that. Oh, I did actually. I've closed it now. Now I'm good. Okay. Thanks, Tom. Okay. That's all right. Thank you. Bye. Okay. Sorry about the further technical glitches, everybody. Learning how to do this on one computer. So just facing a few hurdles, but we should be all right now. So yes, as I said, my name is Jessica Allen and I'm an ESD consultant with Suho. I've been doing air tightness testing exclusively in my role for about 2 years, and I thoroughly enjoy it. It's a very interesting job, takes me lots of different places, and I've learned a lot while I'm doing it. So I will answer questions at the end. Hi, Lissy Camboim. I hope I pronounced that correctly. I'm going to try and keep an eye on the chat while I'm talking, but I probably won't be able to answer questions as I'm going because I'm concentrating on what I'm saying. But I'll get to the questions at the end. Yeah, also, as I tried to explain earlier, this presentation is not in full screen because I'm having some dual screen issues with communicating with our broadcasting software. So I'm just going to use a backup plan, which is just to have the presentation in non-presentation mode and make the screen as big as I can. And we're just going to press on. Okay, so all of our webinars are eligible for a CPD point. So thank you for joining us. If you're here for your CPD, I hope you learned something today. And if you would like your certificate of attendance, please contact us at info@suho.com.au and I'll get that certificate back to you within a few days. So when talking about interpreting results for air tightness testing, there are 3 main things to think about. The first thing that changes the way we interpret results is how we measure the size of the building. If we're using envelope area or if we're using volume, those 2 things then have an impact on the way the airflow is converted into a result. So I'm also going to be talking about the difference between air changes per hour and permeability. And then I'm going to talk to you a little bit about the different types of testing and why the results out of the different types of tests mean different things. So here is a beautiful little picture of a box. Let's just pretend that this is a house or an office building or any kind of building that you could air tightness test. So the dark green external section, this is what we refer to as the envelope area. The surface area in square meters of the walls, the floor, and the ceiling or the roof, the uppermost air barrier. And we use the dark area or the surface area to convert the airflow that's required to pressurize the building into a permeability score. So that is represented as cubic meters per hour per square meter. The benefit of doing it this way is I can type while I'm talking. Cubic meters per hour per square meter. The light green section is the volume of the building, and we use the volume of the building to convert the airflow that's required to pressurize the building into an air changes per hour score. Per hour, here we go. Very good, I can add to my presentation as I go. And that is the amount of time it takes for the entire volume of the building, the air in the volume of the building, to be completely replaced with outside air. So the permeability score refers to how permeable the envelope is, how much air leaks out of every square meter of the building at 50 pascals. The volume is more a reference to how quickly the building inside is replaced. So they are both measuring air leakage, but they're measuring them in different ways. And the reason that we make the distinction is that you will hear these two terms both used when talking about air tightness testing. Permeability is more often used in a commercial setting for larger office buildings, warehouses, hospitals. It's referred to in the Green Star guidelines. It's referred to, permeability is used in the new building code. It's probably the more common way of talking about air tightness. It's much more comparable across different building sizes. When you talk about air changes per hour and use the volume measurement of a building, that's more commonly used in residential setting. In a house, for example, passive house use the volume or the air changes per hour to interpret their results. You can turn any air tightness test either into a permeability result or an air changes per hour result. You just have to divide your airflow by the correct number. It's a very simple division sum. Once you've got the envelope area or the volume, it's very easy to do. You can even take a really good estimate whilst the test is going and impress the client with your fabulous skills and estimation prowess. But the reason that permeability is more often used rather than air changes per hour across larger buildings is because as your volume of the building gets larger and larger, it's disproportionate to the envelope area. So you might have a building that's an office building that's got a very large volume, but the envelope area doesn't increase at the same rate. So if you divided the airflow by the volume of the building, which is quite large, you might get a result that's misleading because the air changes per hour result would be quite low in comparison to dividing the airflow by the envelope area, which would give you a higher result, but it's more accurate. So it's a little bit hard to kind of understand and explain, but basically what you really need to know is that permeability is more accurate and it plots buildings on a much more comparable scale across the globe. Air changes per hour is more commonly used for passive house and residential applications, and air changes and permeability on a residential setting are more or less the same because the volume and the envelope area are usually quite similar. But as buildings get larger, the volume and the envelope area become quite different. So the general process when doing an air tightness test is, firstly, someone like me, your tester, will work out your envelope area and or your volume. It's easy to do both. You can represent the results both ways if you like. So someone like me will take your plans and we'll work out the envelope area and the volume of the building. Then on the test day, we bring all of our equipment to site and we pressurize the building to 50 pascals and we get an airflow reading as to how much air is required to get to 50 pascals in that building. We then divide that airflow, which is measured in cubic meters per hour, by either the volume or by the envelope area. And then we would either get an air changes result or a permeability result. So let's just say if we're doing permeability, for example, this is just a stock image from the internet that I grabbed just for make it pretty. But let's just pretend that this requires 12,000 cubic meters of air to pressurize to 50 pascals. And let's just pretend for argument's sake that the envelope area is 3,000 square meters. So you would divide the 12,000 cubic meters by 3,000 square meters, giving you a permeability of 4. That's really as simple as it is. It's a very simple division sum. So I hope that that clearly explains, or maybe not so clearly explains, the difference between permeability and air changes results. They are both useful numbers, but they are different in application. So yeah, some people really prefer to use air changes per hour because it's a much more, it's very much easier to understand, to think about how quickly the air in the building is being replaced than how much air is leaking out of every single square meter of surface area. It's a much easier concept to understand and to explain. So some people really prefer to talk about air changes, but permeability is probably more common in the larger, broadly across the industry, internationally as well. So I'm just going to take out that section. So there are different ways to test a building and different ways to interpret the results. So this is really important to understand, particularly in office buildings, because if you're getting an office building tested, it's actually not as useful to get a small part of it tested as it is to get the whole thing tested. Now that might stand to reason, but when a lot of clients come to me for their large building testing, they only really want me to test a small portion of the building, and that's generally Green Star clients, hence the Green Star reference in my slide here. They just want a small test and they want to get the point associated with that test. That's generally why clients come to me for large building testing. The smaller compartment tests, though, have their place. They definitely have their place. You can find out a lot of really useful information about the construction of a building and the performance of the envelope by doing smaller compartment tests. But the results that you get are not usable in terms of plotting them against, comparing them against other international buildings, other results. And the reason is that when you are dividing the airflow, so let's go back and we'll get to this stage. So your tester, when you're calculating the external envelope area of a building, if you're only testing a small portion of that building, you only need to calculate the envelope area that's facing the outside air. So if you're testing, for example, a middle floor like this one, you would only calculate the envelope area of the external walls. You wouldn't include the floor or the roof of that level because you don't really care what moves in between levels or in between rooms, for example. You only care what moves in and out of the building envelope. So once you get to this bit and you're dividing this bit here, and you're measuring how much air it takes to pressurize a building to 50 pascals, and then you're dividing it by your envelope area, you've got a much smaller envelope area to divide by, which means that the number that you get, this number here, this might only be, let's just say you need, I won't go into random sums now, but if you're dividing the air that's required to pressurize one level by only the external envelope area, then you're getting a very skewed result because firstly, you're measuring air that's moving in and out and in between levels, and you've got a much smaller external envelope area. So the airflow number that you get and the external envelope area number that you get are totally irrelevant. And those are the two things that you need to get an accurate air tightness test. You need the airflow, you need the envelope area calculation. And if the two numbers that you're using don't mean anything, then the result doesn't mean anything. So when you're doing a smaller compartment, like this diagram shows, you've got air leaking out into the atmosphere, and you've also got air leaking into neighbouring levels or rooms. This is a very basic drawing I made myself, and I think it illustrates the point. These sorts of tests are useful in the way that they will show you where the air leakage pathways are. You can go around with a smoke machine or some little pieces of string or a thermal camera if the conditions are right, and you can actually identify a number of air leakage pathways. And I've done this on a number of occasions for clients, particularly in refurbishing projects where the client wants to know how the building is performing before they make any changes to it. It's really useful to do that kind of testing. But in terms of actually getting a number and being able to plot it on any sort of normal practice, best practice, chart or graph, this kind of testing is not for you. It doesn't work. This kind of compartment testing can be useful in isolation rooms, like, for example, operation theatres, storage areas in museums where there's very particular requirements for the air, for the environment where expensive artwork is being stored or something like that. In that instance, you do want to know exactly what's happening within one small compartment in a building, and then this kind of testing is appropriate. However, if you want to know what the performance of an entire building is, then testing it piece by piece is not going to give you the information that you need. I guess this is an example of a compartment test that I did, and we were asked to only test this section. And I brought it to the attention of the clients at the time that this was not going to give them the right information, and we were instructed to proceed anyway. So this building was actually one of the very few buildings I've ever come across where it was impossible to test as one building anyway. The whole roof was connected as one very large section. This was an outdoor area. So this side of the building and this side of the building were connected by one roof structure. And as you can see here, they had slotted roof tiles. So when we came to test this part of the building, the air was simply shooting up into the roof space through these roof tiles, I don't have an extended picture of this building, but all the way through. So this section here correlates with this part of the building. The air was coming up through here and then traveling out through these wet areas, over across here, and just swirling around in the roof space and just basically escaping everywhere. So there was no way we could effectively test the integrity of this one room. This building had an envelope area of 370 square meters, so it's quite it was just a small little gymnasium area, but it took us nearly 34,000 cubic meters of air to pressurize. So you can just imagine we had 3 fans going in here full blast in a small room, no bigger than a very small house, and we had 3 fans full blast, and I don't even think we still didn't achieve the correct pressure. This was an extrapolated result. So these numbers mean absolutely nothing. A permeability of 91 is absolutely absurd, and it's not accurate because there was air escaping out everywhere. In this instance as well, the ceiling tiles aren't even the air barrier. The roof is the air barrier. There was an attempt to separate this section of the building from the rest of the building up in the roof space. It was not effective. So this is an example, a very extreme example of where compartment testing is absolutely useless. I'll take out the reference to Green Star again. So another way you can test small portions of a building is by doing a guarded test or a co-pressurization test. So very similar to the first kind of test I mentioned, except instead of allowing air to escape through internal floors and walls, you're co-pressurizing those neighboring zones. So you've got a test zone and you've got the neighboring zones or the guard zones, and you've got equipment in the red section here to test this section, and you've also got equipment in here co-pressurizing, which means that the airflow through the internal surfaces is being neutralized, and you're only going to be calculating or quantifying the air that's leaking out of the external surfaces, the envelope area that you're trying to actually test and measure. So if you would like to only test a small portion of a building, and you want the numbers to mean something, this is how you do it. You have to neutralize the internal leakage. The problems with this kind of test, the compartment test and the co-pressurization test, are that particularly in large complex office buildings, you've got a lot of ducting and vents and lift shafts and mechanical risers and all sorts of complicating factors that are going to carry air from room to room and level to level, and you don't necessarily want that. In fact, you probably don't want that if you're testing a small portion of a building. So there's a lot of time that is spent preparing a section of a building for testing. So that can get, time is money, so it can get expensive. This kind of testing as well, you also need a lot more equipment because you have to have guard zones as well as a test zone. It's also, the level of skill for this kind of testing is also a little bit higher than your standard test. So you have to know a lot about the mechanical systems, or you have to have a pretty good relationship with the mechanical contractor in order to make sure everything is prepared correctly. This kind of testing can be really useful, for example, in really large hospitals where there's no way on earth you could possibly test the whole thing. Firstly, because the buildings are just too large, and secondly, because the air tightness testing industry in Australia is still quite young, and there's just not enough people in this country that have got the equipment. There's a couple of contractors that have larger amounts of equipment. For the most part, contractors have only got 1 or 2 fans, and testing a very large building with 2 fans is usually not possible because the building is either too large or it's too leaky. And that is why compartment testing is used, because 1 fan, you can test a small portion of a building with 1 fan usually. And a lot of air tightness testers will try to push this and say it's a really, it's just as good as any other kind of test, but it's not. So just be mindful of that when you're engaging. If you're out to get an air tightness test, just be mindful of that when you're engaging your contractor. Just look at the strategy that they're using and how it fits in with your project requirements. This is an example of a co-pressurization test that we did. This building was permanently compartmentalized down the middle, and so we tested each side individually. I haven't color coded this, but we just swapped. One side was the test zone, one side was the guard zone, and then vice versa. One of these was clearly a lot leakier than the other one, but this test told us where the leaks were coming from. And the doors and windows in this project, across the board, we did a number of buildings on this site, and across the board, the doors and windows were excellent. The installation was good. The quality of the product itself was good. But we discovered where leaks were coming from, and it was all through the walls, the building wrap. So as I said earlier, the results of a test like this can be plotted on a graph. You can decide whether this is normal practice or best practice. Now, neither of these are anywhere near best practice, but the idea of a guided test is that you can use the numbers. The best way to test any building, whether it's a small house or whether it's a very large office building, the best way to test a building is to do the whole thing all at once. All buildings are systems, and they should be tested as a system. Again, I did this presentation for a Green Star audience, as you can tell, but this information applies to the whole industry. Anyone who's getting an air tightness test done, this information applies to you. The main audience in Australia is the Green Star audience because it's under their design and as-built guidelines. They can get points for it, but it applies to anyone. So yes, as I was saying, a whole building test is the best way to get a air tightness test done. It has the highest level of accuracy compared to other projects. All of the internal leakage is taken out of the equation, with the exception of, you still have issues like lift shafts, which go down to basements. because obviously the line between the condition level and the basement level, there's going to be a lift that's going to go through both of those levels, and that's usually a point of weakness that I have found, is that air leaks between basement levels and condition levels at the lift shaft. Just as a little hot tip. But because this kind of testing is measuring as much of the external envelope as is possible, it means that the number that you get is usable. So yeah, so now we've covered envelope area versus volume, we've covered permeability versus air changes, and we've covered the three main types of testing. There is one other type of testing, which is testing only a facade, which is like an even smaller version of this kind of test, but won't cover that one today because I have never had to do it, and that's more of a test of an individual product than of building performance in my experience. So I hope that was useful. Just a nice quick summary for you on how the results of an air tightness test are converted into something usable, and if you can't convert your results into something usable, what the benefits then might be. Our week 12 schedule is yet to be, I think it's going to be released later today or tomorrow, but this is basically what we've got lined up for next week. I'm going to be doing a thermography session on Monday, and then we've got some commercial code changes stuff, a session on material selection for our 10-star home, designing smart walls for energy efficient buildings, and a Hubble demonstration. Hubble is our star rating predictive software that we've developed in-house. So thank you very much for joining me today. I hope that today was useful. Let me see if I can get to any of your questions, if there are any. Let's see. I guess the sound kind of came back on for you, which is great. Let's see. Would you need many fans to do whole building test? Thanks for that question. That's a good question. The number of fans you need depends on two things. It depends on the size of the building, and it depends on how leaky the building is. So if you had a very large building that that had a really good air barrier, there was a really good design strategy and construction strategy around making sure that was a really tight air barrier, you potentially wouldn't need many fans to test that building. And there's a calculation that we use. It's a bit of guesswork that goes on when we calculate how much equipment we're going to need for an air tightness test of a large building. We have to assume what the results are going to be in order to estimate the amount of air we're going to need, therefore the amount of fans we're going to need. So to answer your question, a large airtight building can require a lower number of fans, or conversely, a small, very leaky building can require lots of fans. So for example, I did an air tightness test of a probably 40 or 50-year-old house in the Adelaide Hills recently. It's very uncommon to need more than one fan for a house, and we couldn't achieve 50 pascals in that house, which is the level of pressure that's required to calculate the results. We couldn't achieve 50 pascals in that house with 2 fans. So this is your standard residence in the Adelaide Hills, but we needed a lot more fan power than we estimated, because it was leakier than we estimated. On the other hand, you could possibly test, for example, in my slide up here, this large office building, if it's only got a permeability, if it's a permeability of 4 is quite airtight, it's quite good. And if it's very airtight and you don't need much air, 12,000 cubic meters is about 1.5 to just over 1 fan, 1.5 fans, for example, worth of airflow. You can test that whole building with 2 fans, providing you don't have any pinch points, or providing you can achieve an equal air pressure across the entire building envelope. You could potentially not need much equipment at all. So it's very much dependent on the quality of construction and the size of the building. Okay. Okay, I think that's all of the questions. Thank you, Lissy. And I hope I have pronounced your name correctly. Thank you for joining us today, Lissy, and everyone else out there who is watching now live, as well as anyone who watches this program on replay. Thank you for joining us, and I apologize again for the technical difficulties, but we got there in the end. Sorry you can't see my face. I'm going to try and get this laptop sorted before Monday so that I don't have this same problem again. And I hope to see you all again next time. Okay then. Bye-bye.